This program does not work in C language. You just translate that line by line to Fortran, for example, this program works. No problem. Actually, in Fortran, it would have printed I equals 456 and j equals 126. In C, it does not. Okay. I mean, is that clear that there is some funny business which is going on in C language? That is first question. Any questions on that? That there is a funny business which, this is not what you expected, right? I mean, is this what you expected? On the face of it, we don't expect this, right? But that is what exactly happens when you enter this, compile this program and execute it. So then we'd like to ask some serious, fundamental, basic questions like, first of all, why this does not work? It doesn't work. I mean, what I have given, you enter it on any machine you like, this is what you're going to get. And there's no questions on that. Take my word for it. In fact, you don't even have to take my word for it. Please, you can derive it yourself. That is the first thing I think we should prove that it does not work. Shall we do that? I think that will make it clear. First, we'll prove that this is what you are going to get when you run this on any machine. Then I think I will ask some other embarrassing questions. Actually, the question is not that why it does not work. That is a very simple statement. We can just look at that by simply working out. Remember, we've been compiling these programs. So far, we have been linking the programs. We have seen the compilation process, linking process. One of the main jobs of that, why I have done that, is for you to be able to create what I would call a stack picture. Stack picture. So, why don't we just create the stack picture as the stack gets built up during exact time. I suppose before main the CPU was doing something and it came there. The operating system has directly or indirectly invoked the main procedure definition and we don't have that piece of code here. So let us start the stack picture. It's like a movie, you know. Stack is like a movie which keeps on changing. It's a moving picture. Sometimes it is very moving also, you know, stack picture. So we would like to start that somewhere here when the CPU enters this open brace. Okay. So that is the time that we have. That means some procedure definition invoked this main procedure definition because of the operating system wanted to start this particular program. So the first thing that you see on the stack itself. So let's say this is the stack memory. Now I don't know. See, the SP register has got some values. We don't know what it has really got. What you could do perhaps is, I would like to see, it's always easy to understand if you write some absolute addresses. Okay, these absolute addresses has no meaning at all. I'd like to write some addresses for your understanding only. Later on, you say once you understand this picture, you can just rub off those addresses. So what is the starting value of SP when the CPU entered that? We'll just put some value for it, just to understand that. Shall I say that is 6,000? Is that the standard number that we use or 7,000? 6,000 is some value. It doesn't really matter what you write there. You know? You can write 6,600 also. In fact, probably the correct value of the stack pointer when the CPU enters this open brace is something like a few billions. Okay, we'll see the actual value of stack pointer or the actual likely values of stack pointer at a later session. I'll discuss that. But for the moment, is actually any value assumed here is totally immaterial. So it was this value at which time, of course, the main procedure was invoked. So this is the return address from main. Obviously, the call instruction is going to automatically push the return address on stack when the CPU executes the call instruction. So the return address from main gets pushed as a first item when the CPU lands up at this place. And therefore, this return address itself is a 4-byte address. So it's going to get pushed at the address 5996. Correct? You have to reduce the stack pointer by 4 and that gets automatically stored because of the execution of the call instruction by the central processing unit. And what is the first instruction that we execute when we enter the main? In fact, what is the first instruction that we execute when we enter any procedure definition? We do the push.address frame pointer. I mean, there's always standard. So therefore, we are just pushing the main caller's frame pointer. Actually, I don't know who it is, whoever it is. Main caller's frame pointer. Apparently, there's somebody who calls main, so that fellow's frame pointer gets pushed at address 5992 because that's again a 4-byte value. That's the first job that we do. And once we do that, what is the next instruction of the procedure definition is to copy off the current value of the stack pointer, whatever that is, as the frame pointer, which is the reference for this particular procedure definition. So that means this 5992 is actually equal to mains frame pointer. You just write a comment saying that mains frame pointer now has got a value of 5992 because that's the value we put into the frame pointer register at this particular point of time, at exact time of course. And since main requires 3 local symbolic references, so it's going to allocate memory for 3 locals. So that I suppose is allocation of locals. Actually, there is no specific order that you have to do it. So why don't they just put them in the order they appear? So I is going to be allocated at let's say 5990, J at 5988, and the k at 5986 maybe, okay. So just putting those sub dot a 6 comma sp and contents of, see, remember fp is 5992, contents of fp minus 2 is the first local, contents of fp minus 4 is the second local, contents of fp minus 6 is third local. So we have seen how to access locals. Local n is contents of p minus sigma k equal to 1 to n size of local k, correct? So that the equation is satisfied here, no questions asked. That is how the C compiler works. And once he does that, now of course he's going to assign values to I equal to 123 and 456. I suppose these two boxes will get the values 1, 2, 3 and 4, 5, 6 because that's how they are symbolically referred as part of this main procedure definition, correct? Those two values will go and sit there. And now printf, unfortunately we don't even know what is the meaning of this double quote. So we'll hang the printf for the moment. See, even if you didn't have these printfs, supposing you don't have the printfs, still this program is not going to work. Only thing is we couldn't see it on the screen. The printf is only a mechanism for us to see the result on the screen. But actually the result is wrong anyway. So why don't we just comment off this as far as the compilation process is concerned? We can just comment off this printf statement saying that I don't know how to compile that, so let's just hang it for the moment. So just comment it off. Okay? // will always comment off. So the next statement that we need to execute is the swap I comma j, and when that is a procedure invocation, we know what the C compiler generates is to push the parameter values in reverse order. Don't forget, C always does call by value, correct? So it pushes the values of the parameters onto the stack in the reverse order, correct? That's the behavior that we have seen. And for example, the value of j is pushed first. What is the value of j? Is contents of p minus 4 is 456. That 456 value is pushed. Now don't think that j is pushed. J is not pushed. J's value is pushed actually. And what you push as a second parameter really should go by the name y, because that is what is the parameter which is going to be used by the swap as the second parameter. Similarly, we are pushing the next value is 123, which is really the x value that we are pushing. Value of x is what we are pushing. And these two, of course, are 2-byte values. So 5984 and 5982 contain these two values, 123 and 456. And then, of course, the call instruction is issued, at which time, obviously, the CPU automatically pushes the return address on stack. So this is the return address to main, correct? Return address actually should say from swap, because today main is calling swap, tomorrow somebody else may call swap. Swap, because of modularity, anybody can call swap, right? So this is the return address from swap is the next which is pushed, and the CPU now reaches this open brace of the swap procedure definition. And the first thing that fellow does is, of course, again say whatever the frame pointer value which is there currently in the frame pointer register, the caller's frame pointer is going to be saved. So actually the value 5992 itself is pushed on stack. I mean, that is actually the swap's caller's frame pointer. I mean, the value, if you want, we know the values, I wrote it. Actually, it is swap's caller's frame pointer. I wouldn't call it main's frame pointer because swap's caller could be anybody, correct? So the actual value is 5992, but it could be anything. Anybody could be calling the swap. So swap should only say my caller's frame pointer, who it is. Today it is main, tomorrow it is name. I don't know who it is. So who it is. So his frame pointer value has been saved. And the third thing that he does is to allocate memory for the Z itself. It's a local. So he's going to allocate memory for his own Z, which is contents of P minus 2. And of course, after, I think this is the 5978, 5974. Was that correct? Yeah, right, 74. And this, of course, this is the value of the swap's frame pointer. Swap's frame pointer actually is 5974, and contents of FP minus 2 is actually his Z, and contents of FP plus 8 is his X, contents of FP plus 10 is his Y. So that's how you got the standard representation for locals and the parameter access from procedure definitions, correct? Is that right? I mean, all those things have to be satisfied. I mean, this is a picture which I'm sure you would have drawn if I had asked you to do as an exercise. But I need the help of the picture, so I'm drawing it myself. So I've done it fast because we know this, right? Yeah, now let's go and execute these couple of statements. The first thing is this: I'll take the value of X and throw it into the Z box. And his value of X is this 123. So this 123 comes into the Z box. Next he says, I'll take the value of Y and throw it into the X box. So he takes this 456 and throws it to the X box. And finally copies this 123 back into the Y box. So actually Swap is doing his business. Once you do those three statements, actually the 1, 2, 3 and 4, 5, 6 do get interchanged. But then the first thing that happens when you return back is that fellow is going to swap these parameters. Remember, what you swapped is actually X and Y and not I and J. When you go back and print up I and J, remember they're still having 1, 2, 3 and 4%.